So today we'll see next topic, minimal set of functional dependencies and keys, and that is again from database design. And the minimal set of functional dependencies are actually needed when we design a relational database by using synthesis approach or bottom-up approach. And today's outline will be formally defining minimal set of functional dependencies, and we'll give an algorithm to find minimal cover, and we'll see some examples, and finally we'll go to an algorithm to find key. So minimal set of functional dependencies, let's formally define it. So we know that suppose we have a set of functional dependencies f, then we'll be able to find f plus, which means closure of this f. So how we can find closure of a set of functional dependencies? We start with the given set of functional dependencies and we apply inference rules to expand the set. Okay, so we have IR1 to IR6 rules, and that will be applied on this f to get f plus, which means this finding out this closure is an expansion procedure. Okay, and now we think in the opposite direction to see if we could shrink or reduce the set f to its minimal form. Okay, so that is just opposite of this closure set. Okay, that is actually expansion of the original set of functional dependencies. Now we are trying to shrink or reduce the set f to its minimal form. And what is the purpose of doing this? We are shrinking or reducing the set f to its minimal form so that the minimal set is still equivalent to the original set f. Okay, so how we can shrink f into minimal form, that we will see later, but the actual idea is that even though you reduce f to its minimal form, it means that it should be equivalent to the original set f. Okay, the dependencies should not be violated or destroyed. We should preserve the dependency. And minimal set of functional dependencies, again informally a minimal cover. So we'll go to a minimal cover or minimal set of functional dependencies. Okay, so that is a minimal cover of a set of functional dependencies. E is a set of functional dependencies f that satisfies the property that every dependency in E is in the closure f plus of f. Okay, so we have a set of functional dependencies f, and we are trying to find out a minimal cover of this set of functional dependencies, and we can call it as E, and it should satisfy property that every dependency in E. What is E? That is a minimal cover. Okay, so every dependency in E is in the closure f plus of f. So we have a set E, which is a set of functional dependencies. Okay, and we are trying to find out minimal cover of this S. Okay, and what is this minimal cover? That is another set, that is f, and that satisfies the property that E is converted into f. So what we say is every dependency in E is in the closure f plus of f. Okay, that is a condition, and it must also satisfy two other conditions. F must have no redundancies in it. So f will have a set of dependencies. Okay, that is a minimal cover, and that should not have any redundancies. Okay, so that means redundancy means the same dependency appears more than once. Okay, that is not allowed. And the third condition is that dependencies in F are in a standard form. Okay, so F has a set of dependencies. Okay, and this dependencies are in a standard form, or you can call it as a canonical form. And the standard form or canonical form means if the RHS attributes, so a dependency will be something like x to y. Okay. And if the RHS attributes contain only a single attribute, if that is the condition, that is known as a standard form of these dependencies. So we have x to y, and a standard form or canonical form means the RHS will have some set of attributes. Okay, suppose the RHS has a single attribute, then that is known as a standard form. Okay, now we'll see another definition, that is extraneous attribute. Okay, so we'll see what is meant by extraneous attribute. So an attribute in a functional dependency is considered an extraneous attribute if we can remove it without changing the closure of the set of dependencies. Okay, so we are saying that one attribute is an extraneous attribute. So if suppose we can remove this particular attribute without changing the closure of the set of dependencies. Okay, even if we change, or even if we remove that particular attribute from the set of dependencies, that is not going to change the closure of the set of dependencies. Okay, given f, the set of functional dependencies, and a functional dependency x to a in f. Suppose we are given with a set of functional dependencies f, and take an example dependency x to a from this f. Okay, attribute y is extraneous in x if y is a subset of x. Okay, so attribute y is extraneous in x if y is a subset of this x, and f logically implies f minus x to a union x, the set x minus y to a. So which means we have a functional dependency x to a, and we are removing this x to a from this f, and we are adding x minus y to a, because y is a subset of this x. Okay, if y is a subset of x, then we are removing this y from this x. Okay, and x to x, f minus x to a, that is removed, minus y to a. Okay, we are adding a new dependency like this, x minus y to a, that is removing y from this set. Okay, x minus x to a is removed, and we are adding x minus y to a. So in this case, we can say y is an extraneous attribute. Okay, so which means even if we remove this particular attribute, it will not change the closure of the set of dependencies. Okay. Then an extraneous attribute example. Suppose we have a relation schema R with the attributes A, B, C. Suppose a function dependency set F is equal to A, B to C and A to C. Okay, A, B to C and A to C. And what is closure of this? F plus, that is the set A, B to C, and C is not on the right hand side of this, left hand side of any of this dependencies. So it will have only A to C, A, B to C and A to C. Okay, and here we can say that B is extraneous. Okay, so that is A to C, which means A alone can determine C. The use of B is unnecessary, that is redundant. Okay, so we are saying that A, B to C, and we have A to C, and here B is extraneous, because even though we remove B from the set, it is not going to affect, or it is not going to change the closure of the set of functional dependencies. So A, B to C, that is nothing but A to C. Okay, so that is A alone can determine C, so the use of B is unnecessary, or that is redundant. And given F, the set of function dependencies and a function dependency x to a in f. This is the algorithm. So we are saying that here y is a subset of x. So here b is a subset of ab. Okay, there what we say is we are removing this function dependency from the set. Okay, and we are adding function dependency like x minus y, that is ab minus b. So we'll get a to c alone. Okay, this is a to c is the function dependency here. So we can remove b from the set. And how we can find an extraneous attribute. Okay, how we can find an extraneous attribute. So actually there are two types of extraneous attributes. One type of extraneous attribute occurs in the LHS of a function dependency. Okay, and another will be in RHS of this function dependency. And in the case of minimal cover problems, we need to consider only this LHS attribute. Okay, anyway, we'll see both. So we have the case one. Okay, that is we are considering a case where the extraneous attribute occurs in the LHS of the function dependency. So suppose we have alpha to beta, that is a function dependency. Assume that alpha and beta are set of one or more attributes. So here alpha to beta and alpha beta are set of one or more attributes. And case 1, that is with LHS. So to find if an attribute A is in alpha is extraneous or not. So our aim is to find if an attribute A in alpha, that is in LHS, is extraneous or not. Okay. So what we can do is find the set alpha minus A closure. Okay, using the dependencies of f. So we remove this a from this alpha and we try to find out this closure. And what we can conclude, if alpha minus a closure contains all the attributes of beta, then a is extraneous. So what it says is that even though we remove a from alpha, that determines this beta. Okay, so we remove A from alpha and we find out this closure. And suppose this closure contains all the attributes of beta. Okay, so which means alpha minus A can derive or A can determine this beta. Okay, so this contains all the attributes of beta. Then we can say A is extraneous. Okay, and let's see one example for this case. And f is equal to the set p to q, pq to r. And the question is q extraneous in pq to r? Okay, q extraneous in pq to r. So step 1 is find, according to the algorithm, find alpha minus a closure using the dependencies of f. Okay, and here what is alpha? Consider this, we are considering this function dependency. Okay, pq to r. So here alpha is pq. So find pq minus p closure. pq minus p closure is, pq minus p, q is p and its closure is p plus. Okay, and what is p plus or p closure? So we have, what is p closure? From this we have p to q is there and p to r is there. So we have pqr is the closure for this pqr. Okay, now we found out pqr. That is, we have removed q from the set, from this LHS, and we computed its closure. And step 2 is if alpha minus A plus contains all the attributes of beta, then A is extraneous. Okay, so PQ minus Q plus contains R. Okay, hence Q is extraneous in PQ to R. Clear? So here beta is R. Okay, so we are taking one function dependency and we are trying to find out this extraneous attribute. So here we are considering PQ to R and we are checking whether Q is extraneous or not in this dependency. Okay, what we did was we took the left hand side and we removed this Q, that is the suspected person, from there, and we found out the closure of that set. Okay, and P closure is seem to be PQR, and we can say that what is RHS here, that is R. Okay, beta is R. So alpha minus A plus contains all the attributes of beta, then is extraneous. Okay, so here this PQ minus Q plus contains R. Okay, hence Q is extraneous in PQ to R. Q is extraneous. So we can remove this Q. That is the set will be P to Q and P to R. Okay, so the resultant set will be P to Q and P to R. And second case, how to find the extraneous attribute, case 2. Case 2 means this attribute appears in the RHS. Okay, so alpha, again consider the dependency alpha to beta. Again assume that alpha and beta are set of one or more attributes. And case 2, that is RHS, to find if an attribute A in beta is, so here we are considering this beta, that is RHS. A in beta is extraneous or not. Okay, what is the step? Step 1 is find alpha closure using the dependencies in F dash, where F dash equal to F minus alpha to beta union alpha to beta minus A. Okay, so here we are doing the opposite thing. So we are finding out alpha plus, and what we are trying is that we are trying to remove A from this beta and whether it makes any change. That's what we are checking. So we are again finding out alpha plus using the dependencies in F dash, where what is F dash? F dash here is again the same step. We remove this particular dependency and add a new dependency where this A is removed from this beta. Okay, alpha to beta minus A. And what we can say, if alpha plus contains A, okay, then again alpha plus contains A, then we can say that A is extraneous. Okay, we find out alpha plus and we are finding out this alpha plus using the dependencies F dash. F dash is derived from F by removing this alpha to beta from that and adding alpha to beta minus A. And we are checking whether, suppose this closure alpha plus contains A is again there, it means that A is X. Okay. So let's see an example for that. Given again F as the set of dependencies P to QR and Q to R, and we are checking is R extraneous in P to QR. Okay, R extraneous in P to R. So first step is find alpha plus using the dependencies in F dash, where F dash is this thing. Okay, F minus alpha to beta union alpha to beta minus A. So this F dash equal to P to QR, Q to R. So that is the given F. Okay, F dash is F minus. F contains P to QR, Q to R minus R alpha to beta. What is alpha to beta here? P to QR. Union, what happens? P to QR, we are checking for this R. So P to QR minus R. What will happen? We are removing this from the set. So it will contain only Q to R. Union P to Q. Okay, Q to R union P to Q, that is F dash is equal to Q to R and P to Q. So here, what is alpha? Alpha is P. Alpha is P and beta is QR. So find P plus using F dash. Okay, what is closure of this P? P is P to Q is there and Q to R is also there. So closure of P is again PQR. And what we are checking is if alpha plus contains A, then A is extraneous. So P plus contains R. Alpha plus means here alpha is P. So P plus is given here PQR, which contains this A. What is A? This R. Okay. So P plus contains R. Hence R is extraneous in P to QR. Okay. And F is P to Q and Q to R. Okay. Now we will see this an algorithm for minimal set of function dependencies conditions. Okay, so we have some conditions here, and the first condition is every dependency in F has a single attribute for its right hand side. Okay, that is we have a functional dependency and we are trying to find out the minimal set of this function dependency, and three conditions should be satisfied. And the first condition is that, as we said, it should be in canonical or standard form. Okay, every dependency in F has a single attribute for its right hand side. That is nothing but a canonical form of dependencies. And second condition is that we cannot replace any dependency x to a in F with a dependency y to a, where y is a proper subset of x and still have a set of dependencies that is equivalent to F. Which means we should not have this kind of extraneous attributes. Okay, so we cannot replace any dependency x to a in F with a dependency y to a, where y is a proper subset of this x and still have a set of dependencies that is equivalent to F. So we cannot replace any dependency like this. And we cannot remove any dependency from F and still have a set of dependencies that is equivalent to F. So that is a redundancy. So we cannot remove any dependency from F and still have a set of dependencies. Okay. So that redundancy should also be not there. Okay. So we have three conditions. The first condition is it should be in standard form and it should not have any extraneous attributes. And the third condition is it should eliminate this redundancy. And this is the minimal car algorithm. So input is a set of function dependencies E. So the first step is set F is equal to E. So the set of function dependencies we can call as F. And the next step is replace each functional dependency x2, a1, a2, etc. an. So here the right hand side contains n attributes. Okay, according to our minimal cover definition, each dependency should be in standard form. So this dependency x2, a1 to an in F can be replaced by the n functional dependencies x2a1, x2a2, etc., x2an. Okay, that condition is satisfied here. And the third case is for each functional dependency x2a in F, for each attribute b that is an element of x, if f minus x to a union x minus b to a is equivalent to f, then replace x to a with x minus b to a in f. Okay, so this is nothing but we are removing the extraneous attribute b from x. Okay, so here we have x to a and we are trying to find out each attribute b which is extraneous there. And if it is extraneous, we'll remove that and add that particular dependency to the set. Okay, so here we again find out f dash, which is f minus x to a union x minus b to a. B is removed from x, and this is equivalent to f. This will be equivalent to f. Then replace x to a with x minus b to a in f. Okay. And the fourth step is for each remaining function dependency x to a in f, if f minus x to a is equivalent to f, then remove x to a from f. Okay, that is actually redundancy. That is, we have for each function dependency x to a, if f minus x to a is equivalent to f. Okay, we have f and f minus x to a. Even if we remove this x to a from this f, that is still equivalent to f. Then we can remove x to a from it, because that is a redundant dependency. Consider one example here. E is, that is the set of function dependencies b to a, d to a, and ab to d. Okay, so we need to find out minimal cover, okay, or minimal set of function dependencies. And the first step is that it should be in canonical form. What is meant by canonical form? The right hand side contains only a single attribute. So here, when you consider each dependency, that is in canonical form, because the right hand side contains a single attribute, b to a, d to a, and ab to d. So the first condition is satisfied, and the second one is we need to remove extraneous attributes in LHS. Okay, so extraneous attributes in LHS, that is check for AB to D. Okay, AB to D, and remove A and find B plus. Suppose we remove A and find B plus. So B plus equal to, what is B plus? We are removing A and finding B plus. So B to D and D to A and B to A. Okay, so what will happen? B, A, D. So that is B plus. And we can say B plus contains D. Okay, B plus, this B plus contains D. So A is extraneous. Okay, even though we remove A, we get the same right hand side. So that is A is extraneous. So E will contain only, we can remove this extraneous attribute B to A, D to A, and B to D. Clear. And step 3 is we are removing any redundant function dependencies. Okay. So here B to D, consider this case, we have B to D and D to A. Okay. That is B to D and D to A. That implies B to A, because using the transitivity rule. B to D and D to A. So that implies B to A. So we can, what will happen? Instead of these two, B to D and D to A, we can replace that with, that implies B to A. Okay, and which means the functional dependency set F is equal to D to A. So that is D to A and B to D. Okay, because B to D again implies this B to A. Okay, so B to D alone will cover these two dependencies. So we can have D to A and B to D. So we can remove B to A. That directly, these two directly implies B to A. So we can remove that. So the remaining will be D to A and B to D. That is the minimal car. Okay. Now let's look at the second example, that is another set G with A to B, C, D, E, C, D to E. So step 1 is, the first step is we need to convert this into a standard form. So G is splitting this, because the right hand side contains 4 attributes. So that is split into four functional dependencies, that is A to B, A to C, A to D, A to E, and C, D to E. Now, redundant or extraneous attribute in LHS. Okay. So consider C, D to E. So we can consider that only when we have two or more attributes on the LHS. Okay. So C, D to E, then remove the C. Suppose we think that C is extraneous. So remove C. So now we'll find out D plus. If we remove C, we have only D. And D plus, what is D plus? There are no productions that derive, there are no dependencies with D on the left hand side. Okay, other than this one. So D plus will contain only D. Okay, so CD again, that is not going to make any change. So from CD to E, remove D. We are trying with another attribute. Okay, remove D. So now find C plus. Again, C plus will contain only C. Okay, because C is not there in any right hand side. So C plus will contain C alone. So C and D are not redundant attributes or extraneous attributes. Okay. So that is continued here. So we have again A to B, G is A to B, A to C, A to D, A to E, and C D to E. Now we do not have any extraneous attributes here. Okay. Now we have considered, we have A to C and A to D. A to C is there and A to D is there. That we can say it as A to CD. Okay, A to C and A to D we can combine and form A to CD. So we have A to CD is there and CD to E. Okay, which implies A to E. So what will happen? We can remove this A to E from that. So A to E is redundant. So we can remove that. The minimal car is A to B, A to C, A to D, and CD to E. Or F is equal to A to B, C, D, and CD to E. Okay. Now let's see an algorithm to find key of a relation. So input to this algorithm is a universal relation R and a set of functional dependencies F on the attributes of R. So the input is R and a set of functional dependencies F on the attributes of this R. Okay, now set K is equal to R. So we are setting this relation as the key, and for each attribute A in K. So we have this K, which is nothing but the relation itself, and we take each attribute A in K and compute K minus A closure with respect to F. So we have a set of functional dependency here, and we compute K minus A plus with respect to F. And if K minus A plus contains all the attributes in R, okay, suppose K minus A, so we are taking one candidate attribute A and we remove that and finding out the closure. And if that closure contains all the attributes in R, then set K is equal to K minus A. So we remove A from that. Okay. So again we take next attribute A and we compute K minus A plus with respect to this F. And suppose K minus A plus contains all the attributes in R, then we are setting that as the new key. So we keep on doing this until we get, or we cannot remove any more attributes. So which means we'll get the key of this relation. Okay, so we remove one attribute and we are trying to find the closure, and if that closure contains all the attributes in R, then we set that as the key, K minus K as the key. And again from this K minus A we are trying to remove another attribute which whose closure can contain all the attributes in R. Okay, we keep on doing like this until we get the key. Okay, so that is the algorithm. that is for finding out the key of a relation.